Grinch's dog is.
All right, so we'll start with an easy question.
I don't even know this answer.
Oh, it's just for fun.
I can't believe it was. It's not B. It's not B. There's other C.
All right, so you can go ahead and answer that. What's the name of the Grinch's dog?
No.
All right, how we do? Anybody not done? Yeah, the correct answer is Max. Buster was my dog. He's gone now, but he was one of my favorites, obviously. Fido, of course, is generic. Max, Santa Little's helper, of course, from The Simpsons, right? And the only reason I put this up here is because, well, a couple reasons. When my kids were little, we watched The Grinch almost every night, and their favorite part was always the part where the Grinch and Max are going down the hill, and the Grinch is going so fast, the dog's supposed to be pulling him down the hill. The dog, in fact, goes up, and he sort of like, the Grinch sort of catches up to him kind of thing. And I always thought to myself, yeah, that's not possible. Because I like finding fault in cartoons.
The sled was heavy enough.
What? From purely physical, theoretical physics standpoint, no. They should both be accelerating at the same rate, which is why I put it up there. Anyways, let's talk about acceleration. Now, these are notes. Again, you can sit back, you can follow along, you can write stuff down. The best thing that I would recommend is write down what you think is important. That's what I suggest you do. Write down what you think is important. Oh, and I've got... This is no good. All right, let's try again. I don't know, yeah. So, acceleration is like velocity. What kind of quantity is it?
Vector.
Go ahead and answer. Acceleration is like velocity. It is a... I'll give you the answer to improve your average there. It is, of course, a vector quantity. Now, what does that mean? It means it has
Magnitude and direction.
magnitude and a direction. Don't you have to say, oh yeah, at the end?
No, we don't.
No. Acceleration can be positive, which could mean what? Curseness. Okay, these are supposed to be, yes.
Yeah, you have to say.
Really? Why? It says that you can.
We can.
Single question. No. Rebecca Cranston didn't submit their final responses. Holy, this has been a while since I've used this. Okay, this is going to cause me some grief today, isn't it? You know what? I'm going to do this. Let's try again. Everybody go ahead and answer for the name of the Grinch's dog. Yes, it's D. And now you should be able to answer this question, right? Okay, I got to go back and do this, sorry. Okay. Someone still got it wrong. All right. So acceleration is like velocity. I already gave you the answer. You should know that acceleration is a vector because it has size and direction, magnitude and direction. Oh yeah. I wish that would stay open. I don't want to auto hide. Okay, how did we do there? Did we get it all right? Yay! Okay. So acceleration can be positive, which would mean what? Positive acceleration would mean what? And the correct answer is, unfortunately, it's two answers. It's B and C. Positive acceleration would mean right and up. Oh yeah, did I neglect to tell you that? Oh, my deepest apologies. Oh, quit your worrying about your averages. Yeah, you gotta put them both. Let's see if we can get this one. Negative acceleration, golly gee, I wonder what it could be.
Oh my goodness.
Negative acceleration, of course, is going to be
A.
Here.
Okay, there.
yeah, of course. Really, you guys? Negative acceleration means to the left or to the down. Now, here is a hard question. I'm going to press start, and I'm going to give you about 45 seconds. You can talk to your neighbor and see if you can come up with a response. Does deceleration always mean slowing down?
How do I answer?
With
It's either a Y or an N. Let's see. Well, it's a bit of a tough one. I'm going to say the best answer is no.
Oh, yeah.
Okay, so let's just, I see I have some fine print here. Let's just make this a bit bigger and see, right? Acceleration to the left is sometimes called deceleration. We generally assume that objects move from left to right because we sort of live in a, because we read left to right, we live in a left to right world. So we tend to think about things going from left to right. So acceleration to left is sometimes called deceleration, but this does not always mean slowing down. I'm going to do my very best to not use the word decelerate. Okay? Decelerate tends to mean negative acceleration. Can you give me an example of when negative acceleration would not mean slowing down?
You're reversing.
Maybe you're speeding up backwards, right? You put it in reverse, sped up backwards. Or the simplest explanation would just be, do we not say negative acceleration was down, right? If I drop the ball, does it not accelerate? Of course it does. At what rate does it accelerate? Gravity, which is what number?
1.2.
Anybody know the number for gravity?
1.2.
9.8 sound familiar?
No.
No? Okay. Well, gravity's 9.8. So yeah, acceleration down would be negative acceleration, still speeding up. So just be careful here. What have I got here? What's this picture? Oh yeah. Here might be an example. This was sort of what Ryan was speaking of here. If the object is starting out at -5 meters per second and it decelerates at -2, well, what's in a second? How fast is it going to be going?
Negative.
It's starting at -5 and it accelerates at -2. So in another second, how fast is it going to be going? If it starts at -5, -7, right? -7. The acceleration means how much does the velocity change in every second. So there's an example where negative acceleration, deceleration if you will, is actually speeding up. Okay, so acceleration is, if you had to write a definition for it, you would write the time rate of change in velocity. That's sort of the physics professor definition that generally tends to confuse kids. Time rate change in velocity. In other words, how fast is the velocity changing? And I see some fine print here, and I'm guessing that it's got a better explanation. And I'm correct. It's how fast an object's velocity is changing. How fast an object's velocity is changing. It's not how fast it's going, it's how fast its velocity is changing. Okay? Important difference. And I tend to find that most kids they think they get acceleration, they still need some help. Okay? So I need you to sort of think about that a little bit. Another way to describe it is how fast is an object's velocity increasing or decreasing? How fast is an object's velocity increasing or decreasing? Now, here's a really good question that's not a clicker one. And I may not even give you the answer. Does an object's speed need to be changing for there to be acceleration? I'll repeat. Does an object's speed need to be changing for there to be acceleration?
No. No.
I'll say it one more time and then we'll do a show of hands. Does an object's speed need to be changing for there to be acceleration?
Yes.
Hands up, yes, an object must have a change in speed for there to be acceleration.
Actually, that's a trick question.
Okay, hands up, no, an object's speed does not need to be changing for there to be acceleration. Ooh, okay, so we've definitely got a trend here. Who wants to speak on behalf of the no's? Anderson?
Jake.
Jake always speaks though. Go ahead, Anderson. Why do you say no?
An object can be moving at constant speed and turning, and if you're looking at it in a two-dimensional way, it's accelerating in one direction.
Does anyone now want to change their answer?
I don't even know what he just said.
He's saying that if an object's changing its direction, right? Like for example, if I could insert myself into Anderson's words, if you're driving down the highway and you got cruise control on at 100 kilometers an hour, and you go around a corner, and you maintain that 100 kilometers an hour, are you accelerating? And the answer is, yes, you are accelerating. Okay? You will notice that my question, I said, how did I say it? If an object's speed is changing, is there acceleration? Did you notice that I switched from velocity to speed? Because what does speed refer to? Without a direction, whereas velocity refers to with a direction. So yes, if the speed changes or the direction, you've got acceleration. Well done, Anderson, and the rest of you said no. Yeah? You're just being the opposite? All right. So here's another way to think about acceleration. It's how fast you get to how fast or slow you are going. It's kind of a confusing way to say it. How fast you get to your top speed. Think about a big truck, big delivery truck, and a motorbike. And they're both at the red light, and they each have, let's say, a top speed of 150 kilometers an hour. They probably don't, but let's say. Which one has greater acceleration? The motorbike or the big truck? Definitely the truck, and then I hear motorbike. Who thinks the motorbike has greater acceleration? Okay, I'm quite a majority. Who thinks? Didn't you say truck? Oh, anyone say truck? Of course not, right? The motorbike has a great acceleration. It gets from 0 to 150 much faster. It goes, meow, and the truck goes like this, right? Will the truck ever get to 150? Yeah. Will the motorbike ever get to 150? It just gets there a whole lot faster. It has greater acceleration. Okay. Now, here's a good question. I'm hoping that you've seen it from grade 9 or grade 10 science. Which one of these is the equation for acceleration? And you might want to write down the correct answer when we're done here. Which one of these, is the correct answer for acceleration? Okay, well, the correct answer is D. The correct answer is D. Give yourselves a pat on the back if you said D. Now let's just go through them and see what's wrong with them. What about A? A says delta D over delta T. What does the delta mean? Change in. Delta D, change in displacement over change in time. Well, that's actually what? This is actually equal to average velocity, V bar. So that one's wrong. A equals D bar over delta T. Not even a formula. D bar, what the heck is that? Average displacement? Oh, I guess it's possible. A equals V bar over delta T. Not average velocity. It's the change in the velocity over the change in time. A equals delta V over delta T. Acceleration, remember, is the change in velocity over the change in time. Okay. In this graph below, now Kelly, I think, handed out some graphs. If you want to write right on there, you can. You do with it as you see fit. In the graph below, it's also the one you have on the sheet, the displacement graph is a curved line. Excuse me, I'm getting a little bit choked up about this. The displacement graph is a curved line, meaning that the velocity is A decreasing, B increasing, or C staying the same. Okay, that was good. You guys answered that quickly. The correct answer is be nice if they had a little drum roll when I clicked on that, eh? Correct answer is B. How can we tell that the velocity is increasing? And you should know this already. And what, well,
It's going up faster than it's going right.
okay, I'm looking for an answer with the word slope in it.
The slope is positive, the slope.
There's slope.
The slope is changing, is it not? Like if I were to draw a tangent line right here, if I were to draw a tangent line right there, it would be kind of like, well, that's a poor one. But, right, tangent right there would be like that, and the tangent right here, oh, well, I guess I've got, where did my thickness thing go? I don't know. The tangent up here is going to be like what? Like that, is it not? Is the slope not changing? In fact, the slope is not only changing, in fact, I should probably even say that the slope is increasing. Is that not true? Is not the slope increasing? If this is a DT graph, right? If it's a DT graph and it's a straight line, what does that mean? Constant slope, constant velocity. If the slope is increasing, it means it's speeding up. And that is definitely something that you should remember from grade 10. Okay? The slope is increasing. Now, this is definitely a stretch for you. This is new. Since the velocity increases at a constant rate, and I'm telling you that, I can't actually tell from the graph, but I'm going to tell you that it is. I should probably reword it so it says if, but anyways, since the velocity increases at a constant rate, the velocity graph is which one of these graphs down here? Which one of these is the corresponding velocity time graph? Is it A, is it B, or is it C? Correct answer is B, and I'm pleased to see that many of you got that correct. The key to this is the phrase here, since the velocity increases at a constant rate. The velocity increases. So my velocity graph has to be increasing. What's this graph showing? This is actually showing velocity that's not changing. Exactly, Steve. It's in fact showing constant velocity. And this graph here is actually showing velocity that's doing what? Decreasing. Decreasing velocity. And this one here is not the velocity. Do you not see that it's going up? It's increasing. Is it increasing at a constant rate? How do I know it's a constant rate? The line is straight. Anybody got a, if I just say to you, what do you think the next question is going to be? Do you think you have an idea what it might be?
C.
No, the next question.
I think the answer is going to be C.
Oh, it isn't a question. That's too bad. I should have asked this question. So, given this correct answer here of the VT, I'll just ask you without a clicker now, maybe you saw it. What do you think the acceleration time graph is going to look like? It's going to be flat. Okay? The acceleration graph is a graph of the slope of the velocity time graph. If you are writing nothing down today except one sentence, this is the sentence that you need to know. The acceleration graph is a graph of the slope of the velocity time graph. So important that I'm going to underline it with smiley faces. I'll circle it with smiley faces. The acceleration graph is a graph of the slope of the velocity time graph. And I'll explain that a little bit better in a
Does that
second.
mean like if you want to graph?
The acceleration graph is a graph of the slope of the velocity time graph. Okay? Let's go back to that correct answer. VT, and it's a slope like this, right? What's the slope of that line? We don't know the number, but we know that it's a constant. It might be like, I don't know, it might have a slope of 0.4, right? Is it 0.4 at every point on the line? Yeah, how come? It's a straight line, so 0.4, 0.4, 0.4, 0.4. I'm graphing the acceleration, I'm graphing the slope. If it's all 0.4, then it's going to be flat. It's going to be flat. So if I tell you that the slope of the graph is 0.4, this means that the acceleration is a constant 0.4 meters per second squared. In fact, this value right there would be 0.4, right? And if I said that that slope, that m value is 0.4. This means that the acceleration is a constant 0.4 meters per second squared. We call this uniformly accelerated motion. When the hockey team goes out, they all wear their uniform so they look the same. So what does uniform accelerated motion mean? It means that they are accelerating at the same rate, speeding up at the same rate every second. If you start at 0 after 1 second of accelerating at 0.4, how fast are you going to be going? You start at 0. After 1 second of accelerating, you're going to be going 0.4. And after 2 seconds, you're going to be going 0.8, and then 1.2, and then 1.6. You're speeding up, going faster and faster. Don't worry if you don't get it all just yet. It usually takes me a few sort of tries to get everybody on the same page. Sort of up to speed, if you will. Thank you. That joke always gets a laugh, by the way. This velocity time graph is an example of what we call variable acceleration. What does the word variable mean? Changing acceleration. This might be the toughest physics question you've ever had so far. The question is, oh, it's not. No, sorry, it's the next question. Sorry. The acceleration is, this is easy. Whoops, it's the next one.
Caitlin Campbell, come to the office, please. Caitlin Campbell.
This velocity time graph is an example of variable acceleration. The acceleration is A not constant, B constant, C could be constant or not. Yeah. Yeah, I'm hoping, yes, yay, correct answer, not constant, right? I gave you the answer, didn't I? When I said variable means changing, not constant. Okay, well, no, C, no, that's not true. C is absolutely not true. Because here the acceleration is changing. The slope is changing, right? Okay, here's the hard question. This is the one. Does this object ever move backwards? Yes or no? And there's no gray area in between. Does this object ever move backwards? Not surprising, the answers are pretty much 50-50. Does it ever move backwards? Correct answer? An emphatic no. Now, who would like to explain why the correct answer is no? We hear from Jake all the time. Ryan, let's hear from you.
Because if it would move backwards, it'd have to stop first at least.
How do you know it's not stopped?
Because there's no straight line going.
You can stop like for the velocity.
Okay, Jordan, you go ahead.
On the side, it's the velocity meters per second, so just speeding up and slowing down.
How come it never goes backwards, though?
It never crosses the x-axis.
It never crosses the x-axis. Very good. Is that what you're going to say, Jake? In fact, I think what Ryan was maybe trying to say and couldn't quite find the words was that it never goes below. It never becomes 0. Is that what you were saying? Okay, because you were talking about flat, right? Yeah, that's why I was sort of balking at your answer. For it to go backwards, in fact, let's just sort of describe what the velocity is. Well, it's 1, and then it's 2, and then it's 3, and then it's 4, and 4, and 3, and 2, but it never becomes what? Negative. Here, the velocity is always what? It's always positive. The velocity is always positive, which means it's always moving to the right. In fact, I think Jordan said it best when he said it speeds up, and then it actually does what? It slows down, but it never actually stops. The only way it would stop, this is a velocity time graph, the only way it would stop would be if it actually got to 0. Because 0 meters per second, it stopped, right? Make sense now? Yeah? Nod, so yeah, I get it. Because that's pretty important. Caitlin, I need a nod. Was that just I'm nodding because he's asked me to, or I'm nodding because I get it? Okay, good. Okay, wise guys and gals. You're going to have to just draw it somewhere yourself. Draw a velocity time graph with a similar shape that shows the object moving backwards. Similar shape, so it's got to have that sort of curviness to it, but I want it to go backwards. This is Ryan here. He's going to draw for us. Okay, yeah, deep breaths. Don't hyperventilate. I don't have a paper bag for you to breathe into. Oh. Yeah, click on the pen. Yeah, you're good. Yeah. Okay, that's good. Is he right? Jordan says no? Come and draw one, Jordan. What did you say, Dave? You said something. You did. No, she said something about it doesn't say that it can only move backwards. Is that what you meant? Yeah, it doesn't say that it can only be moving backwards.
Well,
Stars are good. Okay, well, let's look at them both. I would say Ryan's right. And Jane is correct in that she said that it didn't say that it can only be moving backwards. Ryan's is in fact moving forward during this portion, slowing down, actually stopping, and then going backwards. What's happening in this portion right here? Let's not use that word. Slowing down negatively, and what happens right here? It's stopping moving backwards, and then now actually moving forwards again. Jordan's is actually doing what? Just going backwards. In fact, it's speeding up backwards here. What's it doing if we assume this is kind of flat? It's not quite, but let's say that this part is flat right here. What does that mean if it's flat? Going the same speed backwards, exactly. Good. Those are both right. I'll take both of those. Okay. Notice here that the slope of the curve is not always positive. Right? So, between points A and B, do you guys have points A and B on your graph?
Yeah.
Okay. Would you agree with me that you would say that the change in velocity between A and B is it goes from 4 to 2, so that delta V is minus 2?
Yeah.
Would you agree? And that time is from 4 to 7 seconds, with the delta T, the change in time, is 3 seconds, giving us an acceleration of, right? 2 minus 4 is my minus 2, 7 minus 4 is my 3, minus 2 over 3, minus 0.67 meters per second squared. And in fact, if you were to draw a straight line between A and B, what would be the slope of that line? Minus 0.67, wouldn't it, right? The slope of the velocity time graph is the acceleration. The slope of the velocity time graph is the acceleration. Now, clearly, the slope here is flatter and then becomes steeper and then flattens out, right? So, in fact, the acceleration is actually changing, isn't it, right? Remember, this is variable acceleration. Objects tend not to accelerate variably. Like when you pull up to a stoplight in your car and you tramp on the gas, does your acceleration change? Probably not. You're speeding up at the same rate. Your velocity certainly changes, but your rate at which you speed up probably doesn't. Okay? The only way that your acceleration might change would be if you put your foot on the gas a little bit and then you slowly sort of increase the gas. That would be an increase in acceleration. Yeah. Am I good to go on? Now, what about these crazy units? The units on acceleration are meters per second squared. Let's talk about this. Let's do some, as Mr. Friesen liked to call it, dimensional analysis. Anybody heard him say that?
Yeah.
No? Okay, so acceleration is the rate of change of velocity, or the rate of change of, the rate of change of the velocity, which is the rate of change of displacement. In other words, crazy math symbols, A equals delta V over delta T, but delta V is equal to what? Delta D over T. And you might even see in some books they write acceleration is delta D over delta T over delta T. And if I were to use the units, and this is what they call dimensional analysis, if I use the units, then what do I get? Well, I get delta D over T. Just look, don't write, just look, because you won't get it if you're writing. I'll give you a chance to write. What's the unit for displacement? Meters. What's the unit for T? Seconds. And it's all over seconds. So I have meters per second. Remembering back to junior high, how do you divide fractions? This is meters per second, meters over seconds, divided by seconds. I put a 1 on the bottom, so it's meters per second divided by seconds. How do you divide fractions? Flip and multiply. So I flip my seconds over 1 to 1 over seconds, and I change it to a multiply. And how do you multiply fractions? Multiply across. Don't say cross multiply, because some people always say that. So it's meters times 1 is meters. Seconds times seconds is meters is seconds squared. Meters per second squared. That's where that thing comes from. Okay? You don't have to understand that. If you do, that's wonderful. Okay? Don't freak out that, hey, I don't get that. But it wouldn't hurt you to have a look back at that, spend 30 seconds thinking about it. Oh, yeah, I kind of get that. Okay? That's probably something you should maybe think back to or look back to. So the units for acceleration are meters per second squared. Am I almost done? How many pages do I have left? A couple more. Oh, yes, I know what's coming next. So my old friend Galileo was the first scientist to clearly understand the concept of acceleration. Okay? He spent a lot of time playing in his workshop with ramps and balls and such. He found that the acceleration of a ball rolling down an inclined plane, which is a fancy word for a ramp, and the acceleration of a falling object were both described by the same mathematical rules. Now, Aristotle didn't believe any of this stuff. Galileo was the guy that sort of figured this stuff out, right? So what he did was he built himself a very, very long ramp, much longer than the ones we were using, like an incredibly long ramp, made it very smooth to reduce friction. I've got a little video to show you here. The church actually put him under house arrest because of the things that he was saying that the church didn't agree with. And the odd thing about it that the professor was talking about there was that it finally gave him a chance because he was forced to stay in his home. He finally looked at some of his old... Okay, so Galileo probably got... Come on, next page, let's go, run out of time here.